Welcome to Deformation of Solids. In kinematics, we often pretend objects are perfectly rigid masses that accelerate without ever changing shape. But in the real world, when you apply a force to a solid material, it deforms. This unit bridges theoretical mechanics and practical materials science. We are moving beyond specific objects, like a single spring with its own spring constant, to measure the intrinsic properties of the materials themselves. This is a high-yield topic across all your Cambridge exams. You will see it in Paper 1 multiple choice, structured Paper 2 questions, and it is a classic setup for your Paper 3 practical. To compare a thick steel cable and a thin steel wire, we must remove the influence of their physical dimensions. We do this by converting the applied force into tensile stress, which is force per unit area. We also convert the extension into tensile strain, which is the fractional change in length. Mastering these two ideas is your first goal. You will also learn to dodge the examiner's favorite trap, making tricky unit conversions when calculating cross-sectional areas from wire diameters given in millimeters.
Next, we look at what happens when materials are pushed to their absolute limits. You will learn the strict difference between elastic deformation, where a material snaps back to its original shape, and plastic deformation, where the change becomes permanent. Cambridge mark schemes are exceptionally strict on vocabulary here. You must precisely identify and distinguish between the limit of proportionality, the elastic limit, and the yield point on force extension graphs. They look physically close on a graph, but they represent entirely different phenomena. Once you have stress and strain, you can find the Young modulus, represented by capital E. This is the definitive measure of a material's stiffness, calculated simply as stress divided by strain. In your exams, you will frequently expand this into a single working equation, force times original length divided by area times extension. Doing it in one step reduces rounding errors. You will also learn the classic laboratory experiment to determine this value for a metal wire, including the precise micrometer measurements required. Finally, we tackle strain energy. Whenever a material deforms, work is done and energy is stored within it. You will calculate this elastic potential energy by finding the area under a force extension graph. For a straight line obeying Hooke's law, this is simply a half Fx, but we will also look at curves, exploring hysteresis to see how materials like rubber dissipate energy as thermal energy when they are repeatedly stretched and released. By the end of this unit, you will be able to calculate stress and strain to analyze materials entirely independently of their size. You will confidently identify elastic and plastic limits on graphs, determine the Young modulus both mathematically and experimentally, and calculate stored strain energy from graph areas. You have all the tools you need. Let's jump into the first topic.